Okay, welcome. Thank you for coming. So there are very few things that we know exactly about many-body systems. But what we have done up to now is to identify what it is that we measure. So there were fluctuations in the case of scattering experiments, and this type of correlation functions in terms of when we look at the linear response of a system. And the two are related, as we will see today. So what we will do this week is to work out general properties, exact results that we know for these quantities that we measure. And when we will do approximations, usually we will be able to satisfy some of these exact results, but not all of them. You need the exact solution to satisfy all the equation, all the relations, the exact results. But it is sometimes it does less harm to not satisfy one exact result instead of another one. So that's part of using your physical intuition and working out what's appropriate for a system. So before I proceed, do you have any other questions? Okay. So thank you for when you look at your notes and you make comments that there are mistakes in the notes. I correct them all the time because eventually these notes should be a book. So it's important to get all the bugs out. So last time we derived this linear response quantity. So one thing I forgot to say is this something that's called the Onsager reciprocity relations. So suppose this is an electrical current. So I'm looking at the, I want to know what happens to electrical current. If I apply a temperature gradient that will couple to the heat current, okay? So then I have an electric current, heat current correlation function. But clearly, suppose I want to know the response of a heat current to some electric field. Then the electric field couples to electric current, or if you want, the vector potential corresponds to couples to electrical current. So I have a heat current, electrical current correlation function. So you see clearly the two quantities are related. The first one, which is the electrical response to a temperature gradient, is called the Seebeck effect. And the other one, that is the response of a heat current to an electrical current, is called the Peltier effect. Okay, so and already that's one exact result that we know that was known before all this formalism. So I will start by notation and various definitions. I'll talk about symmetry properties that are some exact results that we know. And as an example, I will show this equality between density correlation functions. I mean that they are odd under exchange of frequency. We already know this, but I will show this exactly. And that's one of the results that we will need. Then there's this beautiful fluctuation dissipation theorem between fluctuations and linear response. And there's one way to show it, that uses the periodicity, the cyclic property of the trace, and that is used later for Green's functions. So exactly the same proof, there's something analogous and so on. But to save some time, I will go through I will prove the fluctuation dissipation theorem using the so-called Lehmann representation. And I will show this Lehmann representation is a way to rewrite the correlation function in an exact manner that is useful for exact diagonalization, but also very useful to prove some exact results. Like, for example, to show the relation between retarded function and functions defined on the imaginary frequency axis, so-called Matsubara functions that we will describe later. This is a very efficient way of doing this. So I will not. So there are many symmetry properties that I show in the notes, but I mean, you can always go back to them. So first, some notation. So suppose I defined the retarded response of B to AI. Okay, so so BAI of now I will use translation invariance, but it's not necessary here. This is a more general result, T minus T prime. I write this as 2I times chi double prime of B AI of R minus R prime, T minus T prime, theta of T minus T prime. Okay, what will happen? If I do this definition, when I substitute here, you see that I will be able to extend the integral to infinity here because I have theta of T minus T prime. So the T prime integral will go to infinity. And this will be the retarded response. Okay, in other words, I will be able to write that delta B is chi times A. But if I do this definition, what is chi double prime? Let's write chi double prime first. So chi double prime of B AI of R minus R prime T minus T prime will be equal to 1 over 2 H bar. So this 2 cancels. The I over H bar is I over H bar here, times the commutator of B of R T times AI of R prime T prime. And these are always a thermal average, taken as usual on a trace on a complete set of states. Okay, so it means now that if I go to Fourier space, I'm able to write that the response of B of the Q omega is just equal to the susceptibility chi retarded of B AI of Q omega times AI of Q omega. Now you wonder why I did this definition. Well, I'm asking you to remember when we had the spectral representation of a retarded function, namely chi retarded of Q and omega was equal to integral d omega prime over pi of chi double prime of Q omega prime divided by omega prime minus omega plus I eta. Right, a retarded function will have that structure. It obeys Kramers-Kronig. And when you go to time, when you start from this and go back to time, you get this. You remember? So that's why I do this definition here. So it means that when I look at the retarded response, this here, that I substitute here and I get this, you see I have a convolution in R minus R prime and T minus T prime. That's why it becomes just a product when I go to Fourier space. Then this retarded function will have the structure that's expected for a response function. So once it's written this way, and that will be valid very generally when you look at responses, you see that the physics is basically in this Kidable prime. You see this, right? Because this chi has just Kidable prime times theta. So the theta is causality. Right? Well, there's a discussion in the notes about causality. There's some subtleties in quantum mechanics related to measurements, but in our case, since we're just looking at the at the macroscopic responses, I mean, we have strict causality despite all the uncertainties that occur in quantum mechanics. So is this clear? Okay. So now let me discuss symmetries. So we will be focusing on this Kidable prime because that's where one more remark. What happens to commutator divided by h bar in classical mechanics? Usually it's done the other way around. It's a Poisson bracket in quantum mechanics goes to 1 over h bar times commutator. Okay. So this shows that in the classical limit, some of the sum rules that I show here, that I will show for this object, will be valid also in the classical limit. Okay. They're obviously valid in the quantum limit, but they have their classical equivalent that were probably discovered before the quantum mechanical ones. Okay, so when we work out the symmetries, we can work them out on the Kidable prime. Because that's, as I say, all the physics, and it's called a spectral function because when I look, you will see when I do the Lehmann representation that it depends on the spectrum of the many-body system. In other words, on the excited states and so on. So this is the spectral weight, and the spectral representation was what I just erased there. Okay, so symmetries. So this guy here. So what is a symmetry? A symmetry is some operator that commutes with the Hamiltonian. Okay. If it's a symmetry, it means that the Hamiltonian is unchanged by this operator. So what does it mean for us? Well, for us, it means that when I compute trace of some density matrix, e to the minus beta h, or h minus mu n, times some operator O1 and some operator O2, for example. Then you see this quantity tells us that hs minus sh equal to 0. So it means that I can rewrite it this way. I can put equal sh and then I can multiply by s minus 1. I could have done it the other way, but S minus 1. Okay. So if I use that symmetry, rho, remember, is just e to the minus beta h. So if this occurs for h, then it occurs for rho as well. So I can write S minus 1. Now a trace, there's a cyclic property, right? I can, inside a trace, I can rotate the matrices. If you don't, we will use this very often. If you don't remember, try to prove it for yourself. You see, it's not so difficult. So using the cyclic property of the trace, I can put this here. And now I can put S minus 1 here. So it means I can do, I can reformulate all of this in terms of symmetry operations applied on the operators I'm interested in. And even if these are at different times, I can do that because H has the correct property. Okay. So this allows us to find some exact results based on this. So I want to show this eventually, and I want to use time reversal symmetry. So time reversal symmetry is probably the most complicated symmetry in, in quantum mechanics, because time reversal symmetry involves complex conjugation and a unitary transformation. And you can, it's worked out in the notes for spin, where you see, I mean, where you see why it's necessary to have complex conjugation and a unitary transformation. But I will take the simple case. Okay, and a simple case is when there's no spin in particular. So there's no we don't, this unitary transformation is not needed. So let me write the momentum operator. Well, let's do it in the simplest case. So let's go back to elementary quantum mechanics. So P is h bar over I graph. So what happens if I do a time reversal operation? Momentum should go to minus momentum. Okay. So you see that means that I need to take complex conjugation of this operator. You will see that it's because it's self-adjoint that it works out this. We will see this in one moment. If we look in the wave function, if we look at Schrödinger's equation for the wave function, if the Hamiltonian is real, has no complex part to it, then a complex conjugation leaves it invariant. And the wave function will evolve backwards in time if you take its the complex conjugation of the Schrödinger equation. Why? Because there is a IH bar d psi dt. If you do time reversal, there's a minus sign that appears, and you see that is precisely the equation that's obeyed by psi star. Okay. So again, in the notes, I discussed this in a little bit more detail, and make it even more plausible, but that's the sort of the simple way of seeing this. Okay. So time reversal symmetry is another case where, well, another case, it's the only case that I know where the direct notation has some can lead you into problems if you don't take care of it properly. So let's look in general at the expectation value of I times some operator times some other many-body state J here. And let's do the time reversal operation on the wave function. Okay. So if I do the time reversal operation on the wave function, what I want to do is work it out for the operator. I need to do complex conjugation of this. And I call complex conjugation this bit k. Yeah? And here the arrows tell me where it applies. Okay, contrary to the usual direct notation, it does not apply on either side. I mean, it applies to this and to that. Okay, so now what I can do is go, permute this like that. If I k k O star J. Okay. Now when the complex conjugation will remove this and it will act on J. So this is equal to this. Now, if you look at the definition of the bra and the ket, you know that I can write it the other way. So I could write that this quantity, complex conjugation of I was already complex conjugate, so I can, now this bra can becomes a ket, and this ket here can become a bra. So O star J. Okay. But using the definition of the adjoint, then this becomes O dagger star. Okay. So the momentum operator that is self-adjoint, when I do the time reversal symmetry operation, I take the adjoint, that doesn't change anything, and then I multiply by I take the star, so that was okay.
Sorry, I have a question.
Yes.
How is it that K is applied only to in a way or another, and we have to specify it? Why is it that we can permute K and O?
No, okay. I'm doing the time reversal symmetry operation by acting on the wave functions. Okay. So I'm taking complex conjugate of this and complex conjugate of that. Now this operation that is complex conjugation, I mean, here what I have done is trivial. I just commuted the complex conjugation with O, and to have this as an equality, this needs to be complex conjugate, because the complex conjugate of a product is the product of the complex conjugate. Okay. If I have AB star, this is equal to A star B star. Okay. So that's all that I'm using.
Well, why is I and J still on in the same order that it was before then?
No, here I just complex conjugation was acting on this. I just put it on the other side here, so that when the complex conjugation acts on this, it's equal to this.
Oh, okay. I think I get it.
Okay.
Okay.
And then excuse me. Then I just use the definitions of bra and ket and the definition of adjoint. So this is what happens. Okay. So I will use this to show this relation. So we will use two results. One that is a consequence of time reversal. But before that, result that is a consequence of the definition, just the fact that this is a commutator, okay? So, so let's do it generally. So I look at the chi double prime of AI, AJ, okay? I and J here are not related to the ing I just had a minute ago. It's just operator I, operator J. I'm trying to do it generally, okay? And I will, instead of writing all the indices here, I will just write the time, okay? So t minus t prime. So chi double prime of AI, AJ is equal to minus chi double prime of AJ AI of t prime minus t, okay? It's a commutator, so if I inverse this, I just get a minus sign. So you see AI, AG, now I have AJ, AI. And I have t minus t prime, now I have t prime minus t, okay? So what happens if I go to frequency? So I take Fourier transforms here. So suppose I take Fourier transform such that this goes to omega. Now this will go to minus omega, okay? Because the times are the other way. So I have minus omega. Okay, now I want to use the time, this time reversal operation. Okay. So if let's do it slowly. So I have the commutator of AI of t. Let's put t prime equal to 0 to simplify, AJ. Now if I have time reversal symmetry, that means that this should be equal to the commutator of AI dagger star of t times A J dagger star. Okay, I'm using this result that if I have the expectation of an operator, if I have time reversal symmetry, this is equal to O dagger star. Okay. So, and we said that if there are two operators, then it works the same way. Now the density is an Hermitian operator, and I'm going to work with Hermitian operators, but you have to remember if the operator is not Hermitian, you have to be careful here. So let me work with Hermitian operators. Okay. Now, if I take a complex conjugate of the density, it is still the density. So for operators that are real operators, like the density, this disappears. And but then here the star here is non-trivial because A of t is equal to e to the I h t over h bar times A times e to the minus I ht over h bar. So if I take the star here, I have these change sign. Okay. So and that's where you see the time reversal. This becomes minus t. Okay, minus t. Is it okay? So again, if it's density, then it's a real operator, so there's no star. But suppose I was computing current correlation function. Then the current changes sign under time reversal. It's called the signature under time reversal. Okay, the current operator changes sign under time reversal, not the density. So as long as I have two operators that have the same signature under time reversal, that would be satisfied. Okay. If they have opposite signatures under time reversal, then I get a minus sign. So the star will give me a minus sign, like I showed with the at the beginning with the momentum operator. Okay, so what does this imply for this type of correlation functions? It implies that if I have time reversal symmetry, you see chi double prime of AI Aj of omega will be chi double prime AI Aj of minus omega. So I can write this result here. And that will prove what I need to prove for the density. Okay, so chi double prime of AI Aj of omega is equal to chi double prime of Aj AI of omega. So if these operators have the same signature under time reversal, then I can invert this. So here I have chi double prime of AI Aj of omega equals minus chi double prime of Aj omega of minus omega. But now using this result, I can put this back where it was. So I find that this chi double prime is an odd function of frequency that we needed for, remember, for positivity of dissipation. So that's a special case. I mean, I get the Fourier transform of the density and the Fourier transform of Q and minus Q. And that's a special case of combining these two results. Okay. So now we go back to we go to serious things. We go to the Lehmann representation. The next the things I will show what I will show Wednesday tomorrow next time will be some rules. So some rules are related to high frequency behavior of correlation function, which in turn are related to equal time commutators. If you remember, for the harmonic oscillator, we found that at a high frequency, we recovered the non-interacting case. We recovered, I mean, the free oscillation. The mass responds as if there was no friction. So these some rules are related to what we know from equal time commutators, or if you want, of free particles. So the Lehmann representation is a very simple idea. It's just to use a complete set of state and the explicit definition of the density operator to show, to have a representation of these objects, chi double prime. And as a consequence, a representation of chi, because it's simply related. So I erased what I need, but I suppose you remember that chi double prime is just a commutator. So I will drop r minus r prime. And I will just keep these indices I and j. So chi double prime of AI aj is just equal to the 1 over 2h bar times the trace. So the trace I will write as sum over n of n, and then I have the trace operator, okay? But I will work with states here that are energy eigenstates. So if these are energy eigenstate, then I know what the action of H on this. So I can immediately write this as e to the minus beta times the energy of that state n, and we take the z here. Now this is a function of time. Now I have AI of time, okay? But AI of time is what? AI of time is e to the IHT over h bar, AI, e to the minus IHT over h bar. Now let me put a complete set of states here. And I have a commutator also, so I need to not forget that I have a commutator. So I will do the two sides of the commutator separately. So now I have AI of t, and then I will put it on the other side. So now m aj m. Is this okay? And I know the action of h on n and h on m. It gives en and em. So let me use this immediately. So I have AI m aj n times e to the I en minus e m t over h bar. Okay, ein m. Okay. Now this is a commutator, so I do minus e to the minus beta en over z, and then I just, a and j are inverted, so I get n aj m ai n e to the I en minus em t over h bar. And now you see if I just change n for m, these are just dummy indices. So if I change n for m, the matrix elements become the same. This goes to this goes to this. But now n has to go to n, and here n has to go to m, so I'm sorry, this is wrong. I have en minus eny, because ai was here now. So the left acts on m and the right acts on m, okay? Now I think I get it straight. So you see that if I change n for m, this goes to this goes to that, this goes to this, and the only thing that doesn't move is this. So I get 1 over 2 h bar times a sum over n m e to the minus beta e n minus e to the minus beta e m over z times times n ai m m aj n times e to the I e m minus e n t over h bar. So what happens if I take a Fourier transform of this? So suppose I want to know now, I want to know chi double prime a I a j of omega. Now I need to take the Fourier transform of this. So what will happen? I just get a delta function of this, right? And here it should be this, en minus en. Okay, so when I take the Fourier transform, this is just the integral and e to the I omega t dt. Okay. So what is it? What is this? This is delta of omega minus em minus en over h bar. So using a Dirac's representation of the delta function, this is 2 pi delta of omega minus em minus en over h bar. And now I can so this 1 over h bar I can multiply by h bar and then it becomes an h bar in front, and then I get rid of this h bar, and so I get 2 pi, and then the 2 disappears. So the 2 disappears, and this becomes really, I'm a moving board today. This becomes pi times delta of h bar omega minus em minus en. Okay, you already know that this is related to absorption. And this is proven again in this chapter in detail, but you've done this already. So one of the remarks we can do is that there's a Bohr's correspondence principle, in the sense that you see that the absorption comes in at frequency that correspond to energy differences. Okay. Okay, that's one remark. The other remark is the fluctuation dissipation theorem. So you see that I can rewrite En is equal to En Em will be equal to H bar omega equals En minus En. So Em is equal to En minus H bar omega. Okay. So I can rewrite this. Now I'm proving the fluctuation dissipation theorem. So this is En plus H bar omega. So you see that now I can factor En, e to the minus beta n. So this is e to the minus beta En times 1 minus e to the minus beta H bar omega. Okay. So what is this? These are just fluctuations, right? So if I go back to correlation functions, I will just get the expectation value of AI of t, aj. Then I take Fourier transform and it gives this. So that's just the Fourier transform of the AI of t, aj. If I go backwards. So what I have proven, and I can finish with this. Is that the fluctuation that I have previously called S of AI aj of omega is equal to 2 over H bar divided by, so you see this is the e to the minus beta H bar omega times chi double prime of AI aj of omega. So when I compute the fluctuations, the H bars are not there. And when I take the 2H bars not there, and when I take the Fourier transform, I get 2 pi times this. So that's why I have 2H bar here. So that's important. That's the fluctuation dissipation theorem. And you can recognize this as 1 plus the Bose factor. So what happens in the classical limit? What is the classical limit here? Now, as usual, it's when KBT is larger than H bar omega. Okay. So when KBT is larger than H bar omega, it means that beta goes to 0. So I can expand the denominator. And here in the classical limit, becomes kBt times chi double prime of ti ag of omega. Okay, this is one part of the notes that is probably wrong in the way it is in the. Okay, I've tried to derive the fluctuation dissipation theorem classically, and I get into all sorts of problems. It's very easy quantum mechanically, you see. But so the classical limit is well defined here. There's no h bar that comes in, so it should apply in the classical limit. So there are quite a few, but you see quantum mechanically, whether omega is larger or less than 0, it makes a big difference. Why is that? Okay, suppose we look at the scattering experiment. Okay, so remember what is omega? Omega is the energy, h bar omega is the energy, the final energy of the probe minus its initial energy. So if omega is larger than 0, it has gained energy from the system. If omega is less than 0, it has given energy to the system. Okay? So you see that, for example, in the, if we go to 0 temperature, so beta goes to infinity, then this at negative, at positive frequencies, for beta goes to infinity, at positive frequency, this becomes 0. Okay? At positive frequency. So I'm getting this wrong, I think. At negative frequency, then this goes to infinity, and then if it goes to infinity at negative frequency, this becomes huge, so this whole thing becomes 0.
And what happens when the temperature or omega is such that the denominator is 0?
It doesn't happen. I mean, that's this classical limit, because you get 1 minus 1, and then you expand this to linear order. The h bar drops out, and I forgot the factor of 2. The 2 does not drop out. Okay? So as long as the temperature is, I mean, this could go to 0 if beta goes to 0. So you have 1 minus 1. But when beta equals to 0, I have to take the limit, and then it works out. So when you do scattering experiments, your probe can absorb or give energy to the system, and it's different, right? In one case, for example, if you do Raman scattering, if you look at the spectrum for Raman scattering, omega, then there's the Stokes and the anti-Stokes line. Here it has given energy to the system, and here it has absorbed energy to the system, and it's less likely to do that. So if you look at this for plus omega and minus omega, and you look at the ratio of these peaks, it's given by the Boltzmann factor, e to the minus beta h bar omega. So this is another manifestation of detail balance. And you see another way to see this is that quantum mechanically, K double prime is a commutator, and this is also an equal time correlation functions, but these quantities don't commute, okay? So there's a difference between positive and negative frequencies. But in the classical case, no problem, because the two quantities commute. So you always have this equality, and if omega changes sign, then K double prime changes sign. So there's this this aspect. But other than that, it works out. Okay. So you see, if I'm doing exact anglization, this Lehmann representation is very helpful because I mean, I'm computing these eigenstates, and I can compute these quantity exactly. And as I said, it's extremely useful to establish exact relation, like I just did here, the fluctuation dissipation theorem, but also to connect imaginary time or imaginary frequency results and retarded quantities, like I will show later. Okay, so if there are no questions, I will see you in a couple of days. Okay.
Merci, bonne journée.
Okay, si vous avez des questions, if you have questions, you can stay and ask your questions.
Thanks. Bye.
Okay.
Might have a small question.